Corrosion Part 5. Hello everyone, this is Corrosion Audio Lecture 5, Advanced Kinetics of Electrochemical or Aqueous Corrosion. In this lecture I want to look at more complicated algebra for predicting the speed of electrochemical corrosion when we have diffusion-limited oxygen supply, and I want to look at diagrams for predicting the speed of corrosion when we have passive corrosion. These cases are both more complicated than the simple Tafel-limited or activation-limited calculations for corrosion speed, which we looked at in Audio Lecture 4. Before we look at calculations of corrosion speed in complex cases, let me introduce this lecture with this photograph of some corroded cast iron water pipes. So this photograph is taken by the Chicago Transit Authority in 1918, and it's a scan of a photograph that was printed out in a book, so the image quality, I'm sorry, is not perfect. You have to imagine partly what you're seeing here. So let me describe it. What you see here is some cast iron water pipes which have been dug up from underground in Chicago, and they have corroded and cracked, and they've been laid out in this yard exactly as in the same alignment that they've been dug up. So you can see they've all corroded in the same place along their length, or actually in the same two places along their length. And the reason for this is a localized corrosion phenomena we'll look at next time called stray current corrosion. We can describe though the problem using what we know already. We know corrosion of things underwater, including cast iron pipes in wet ground, is an electrochemical process. Now, we know that the metal becomes an anode when it corrodes. Normally, we've looked so far at this happening because of spontaneous chemistry on the surface of the metal, but in this photograph from Chicago we have another reason why the cast iron water pipes can be made to be an anode. And that reason is an applied electric field, or it's called a stray current corrosion phenomenon, instead of spontaneous electrochemistry. How does the stray current corrosion come about in this place? So urban environments are often very busy, or if you look at the underground infrastructure, there's quite a lot of it in cities. One thing which Chicago had in 1918, as well as these water pipes, was a tram line. And electric tram lines, you probably know, these are typically DC systems. So you have a high voltage DC power supply cable which runs overhead, and the DC current was returned typically along the rails on the ground. Now, as far as the electrical substation was concerned, it was pulling a large DC current through the return rails, probably applying a small voltage in order to do so. And it thinks all of this current is being pulled through the rails from the train. But this is not quite true. In reality, there is some electrical resistance along the sections of track of rail, and this particularly comes about because the adjacent sections of rail might not be very well electrically bonded, say by soldering, in which case the substation is pulling DC return current, but not all of it is necessarily coming through the rails because the rails are not resistanceless. Instead, a proportion of the DC current pulled backwards into the substation might be drawn from other places than directly along the track. In this case, in Chicago, we have in this photograph evidence that some of the DC current drawn into the substation was pulled from adjacent metal infrastructure in the ground, such as these water pipes. And where the water pipes immediately crossed underneath the track, you have the bits where the cast iron water pipes were closest to the track become anodes, and an ion current begins to flow which involves dissolving metal from the pipes, and an ion current flows through the ground, discharges onto the rails, which were nicely protected by this process. And that's a stray current. The power supply to the tram system did not intend to apply this current, but nonetheless it pulled some stray current from the cast iron water pipes, corroding them as it did so, and it's characteristic of stray current corrosion that it happens in very precise small areas which are closest to the, in this case, the electrical rails. Once you have this photograph in which there are exactly 2 breaks in each water pipe, lined up in exactly 2 rows where all of the pipes passed underneath the straight tram rails. Okay, that's a more advanced process than we need to do the maths for in this lecture. So what we will do now is develop, using what we know so far, the thermodynamics of electrochemical corrosion, which tell us the driving force, and the kinetics based on exchange current density and the Tafel equation. We want to use that to predict the speed of corrosion in more complicated cases. Case number 1 for this lecture is when we have diffusion-limited corrosion. So this sketch tells me that the limiting factors in my corrosion problem are now both the anode and the cathode electrode activation potentials, so there's Tafel limitation, but there's also diffusion limitation for the supply of some oxidizing agent to the cathode. This commonly applies, as discussed in section 3.7, when you have diffusion-limited rate of supply of dissolved oxygen in aqueous solution to some metal surface. Okay, to model this problem, we have to consider a sketch like this, where we have a linear diffusion boundary layer. So we imagine that we have some probably low bulk concentration of dissolved O2, Cb for C bulk, and we have a linear diffusion boundary layer of some thickness x between the bulk solution and the corroding metal surface, and the oxygen concentration at the metal surface is actually some depleted quantity Ci. So this is the concentration C when you have some current density of corrosion small I, and this is depleted relative to the bulk by some amount which accounts for the net rate of diffusional supply of oxygen, which you can imagine happening by Fick's law diffusion or by linear mass transport coefficient. It's okay to use Fick's law to model this oxygen diffusion because we're talking about dilute dissolved oxygen, which is the common reason why you have diffusion-limited corrosion with dissolved oxygen. Now, what about the algebra for modeling this process? So we have equation 3.26, which tells me that the rate of supply of oxygen to the surface of the corroding metal is given by this diffusion coefficient d times by a concentration gradient. That's if we have Fick's law. This gives me an oxygen supply rate in moles of oxygen per meter squared of metal surface per second. I can convert that using Faraday's law to some quantity in terms of current density, so that's amps per meter squared per second, equivalent to this rate of oxygen supply. It's just a ZF, the charge per mole of oxygen O2 being supplied, times by the expression for Fick's law diffusion. So diffusion coefficient times concentration gradient, which is the difference in concentrations between the bulk and the surface, divided by the boundary layer thickness. What I can immediately say by this is Fick's law shows us that there is some kind of limiting corrosion current density, a diffusion-limited maximum possible rate of oxygen supply. That is, if the oxygen concentration on the metal surface is completely depleted to 0, that's the smallest possible surface concentration, Ci, that I can have. The bulk concentration is a fixed quantity, so I can get equation 3.28, which tells me the largest amount of corrosion current density I can have within diffusion limitation is this I subscript L for limiting current density, and it's this ZFD times C bulk over X. Now, I can do something more useful than this, because I can take equations 3.27 and 3.28, and I can say if the current density of corrosion at the metal surface is small I, then I can get an expression for what the surface oxygen concentration Ci is. And that expression is given after some rearrangement by equation 3.29. and it will turn out that your surface concentration of oxygen is equal to the bulk concentration times by 1 minus the actual current density over the limiting current density. So that's the right-hand-most version of equation 3.29. That's important because it gets me an expression for the effect of diffusion on surface oxygen concentration, and therefore it allows me to work out what is the, in equation 3.30, what polarization on the metal surface arises from oxygen depletion, and I can consider this as a Nernstian polarization term which I can add, literally just add, to the activation polarization for which we already have an expression in the Tafel equation, and those are going to be something I can combine together to work out what is the total polarization of a diffusion-limited electrode. The polarization from diffusion limitation is given by equation 3.31, and we already had equation 3.20b for the Tafel limited polarization of a cathode. Now if we take those over the page, we can use them in an example. The maths for combining these is a bit more complicated, but we can easily plot the results of doing this combination if we look at an example problem. So the question on page 34 is it asks us to determine the corrosion current density of some copper object which is dissolving in aerated acid at pH 0, and it contains dissolved copper 2+ ions and dissolved O2 oxygen molecules, both at unit activity. This is unrealistically high for oxygen molecules, but it just keeps my equations a bit simpler. Anyway, so we assume the anode reaction is copper metal going to copper 2+ ions, and it's an anode reaction releasing 2 electrodes, and I'm going to assume the only cathode reaction is dissolved oxygen reacting with protons in solution and absorbing 4 electrons to turn into water. And I will assume that there is diffusion-limited supply of oxygen in this system. So I'm just looking at one metal surface, so in this case, to solve my problem, I can work out the anode current density equal to the cathode current density for the one anode, the dissolving copper, and the one cathode, the reacting oxygen, and we'll call them both equal to the I core, the corrosion current density, at some steady state. And I'm given my usual data for solving this problem, and in addition to the equilibrium potentials for each electrode, the exchange current density, and the Tafel slopes, I'm also given this I subscript L. I'm told that the diffusion-limited rate of oxygen supply, because of whatever the boundary layer thickness happens to be, I'm told this limiting current density is 2 milliamps per centimeter squared for oxygen supply. Now the solution to this equation is best found by plotting the graph below. But we have equation 3.32, the anode polarization which comes about from Tafel limitation on the copper, and 3.33, this is the total cathode polarization. This includes the Tafel term, and it also includes this diffusion term which we derived above in equation 3.31. And if we add those two terms together, it's difficult to solve algebraically, but we can computationally consider a lot of possible current densities that we might have. We'll plot those along the x-axis of the graph, and for each case we'll plot the we'll use the polarizations to plot the electrode potential for those two processes. And we're looking for the intersection of these two curves, where the anode current density is equal to the cathode current density. So we get a solution. We have this dark blue line for the oxygen reaction and the dashed red line for the copper electrode reaction, and we get this circled solution which tells us the corrosion potential and the corrosion current density. So in this case, this is why we talk about a diffusion-limited. This graph shows us why we talk about diffusion-limited current density. You see that the possible current density which we get to is, it reaches a vertical line, which is a strict diffusion limit. The vertical line can be seen in the oxygen electrode curve, and so this is computationally how we would find out what the solution is, by doing some exhaustive plotting, for example. If you wanted to solve this algebraically, what you could do instead is you could, number one, calculate what in this question you've just been told the diffusion-limited current density is 2 milliamps per centimetre squared for oxygen. Then you could solve the problem using the Tafel limitation alone, the question which we've already done in example 3.6. And you could then say, if the solution for Tafel limitation alone is lower than the diffusion-limited current density, then that's the correct answer. But if the solution considering Tafel limitation alone is higher than the diffusion limitation, then actually the corrosion current density that we have is equal to the diffusion-limited current density. Page 35 comments on how diffusion-limited corrosion rate can be controlled by several different factors. So we have an equation for IL, the diffusion-limited current density. Obviously, it can vary by orders of magnitude depending on what the parameters are. So if we have a dissolved oxygen concentration which increases, then we can have a faster diffusion-limited current density. So the solubility limit of oxygen actually goes down with increasing temperature. So for that reason, higher temperatures would potentially sometimes give you a slower diffusion-limited current density. On the other hand, higher temperatures will give you a higher diffusion coefficient for oxygen, so that might increase diffusion-limited corrosion current. But probably the more important factor is that flow speed, or Reynolds number, affects boundary layer thickness quite strongly, and so frequently when we have diffusion-limited corrosion rate, we're looking at when we have a faster flow, we have a much faster rate of supply of oxygen, a faster limiting rate of oxygen supply, and faster corrosion. So that's something which is looked at in the example sheet questions under flow-induced corrosion. Good. Page 36, section 3.8 is non-examinable. It's actually quite approximate, it's just for illustration. So we have here an indication of how another algebraic term, which is harder to deal with, can affect corrosion speed. So this is, how does the ion conductivity of solution affect corrosion rate? So equation 3.34 considers what happens if you have 4 different sources of polarization or voltage loss in a corrosion cell. If you have the anode and cathode activations, if you have some diffusion polarization because of oxygen, limited rate of oxygen supply at the cathode, and also what if we have some ion resistance term because the corrosion current is relatively large, so the ionic resistivity of the electrolyte is not negligible. So for illustrative purposes, we could write down this approximation. Let's consider an electrolyte of resistivity ρ and some characteristic length scale L, which means that we have an ion resistance polarization given by equation 3.35, just current density times by resistivity times by characteristic length scale L. If we invent a model where we have polarization at the anode, which is the Tafel polarization plus half of this ion resistance term, slightly arbitrarily we'll call it that, and at the cathode we say we have the cathode Tafel polarization plus the diffusion limitation polarization plus half of this ion resistance term. Then if we consider that, we can computationally solve what happens, and we can get a graph. Again, we're looking at the separate electrode reactions, copper dissolution and oxygen reaction in electrolytes of different ion resistivity, and I've plotted curves showing what happens for pure water of characteristic resistivity that's quite high. I've said that's 5,000 ohm meters, and I've said for seawater we've got 0.3 ohm meters. So the main takeaway message from this plot is not the exact curves, it's the observation that we have a couple of orders of magnitude difference corrosion speed, so 2 units on a log base 10 scale for corrosion speed. When we look for the solutions to this system when we have pure water, which is much slower corrosion than we see in seawater. And this is just because of different ion conductivities. So we have seawater being much more corrosive just because the roughly 0.6 molar sodium chloride solution is so much more conductive, hence faster corrosion. Okay, page 37, section 3.9. This talks about the area effect in corrosion models. Now this is potentially, in the real world, this can be the most important thing that you need to worry about. Because in the real world, we often have situations where two different metals are connected. And it may turn out that just one of those metals is hosting a anode reaction where that metal is dissolving, and the other one isn't actually dissolving at all, but it is providing extra surface area in electronic contact with the dissolving metal, which provides a lot of extra area for a cathode reaction like oxygen reaction. So we have this example problem. It says a zinc anode of area 1 square meter is attached to a sheet of iron with area 10 square meters. All of this metal is submerged in acid at pH 0, and it has dissolved zinc 2+ ions in solution at unit activity. We are told here the only significant reactions are the zinc dissolution and hydrogen evolution, which we're told effectively we only need to consider this taking place on the iron surface, because the iron is a so much better electrocatalyst for proton discharge. The example also says ignore mass transport limitation, so ignore diffusion limitation. So the solution for this problem is given below. So we're given the usual data, the standard electrode potential for the zinc. We could get the equilibrium potentials if we were dealing with a non-unit activity solution, but we don't need to here. The equilibrium potentials are just equal to the standard electrode potentials. We're also given the exchange current densities for the zinc and protons and the Tafel slopes for the zinc and proton reactions. So the solution, how do we do this? Well, we say we have spontaneous corrosion on a block of metal, so the whole surface of the metal is at some surface potential E. We know that we have steady state dissolution, so we're looking at no charge accumulation and Tafel-limited kinetics on both electrodes. So we write down an equation where we have the current through the cell is equal to the anode area times the anode current density, and that has the same absolute value as the cathode area times the cathode current density, all as absolute values. So we then write down the Tafel equation for both sides. We rearrange and solve, and because the Tafel slopes are equal in magnitude in this case, this is pretty easy to solve, and so we solve and get E, the surface potential, minus 0.2 volts SHE, and then we solve and get the corrosion current density. Now we get the anode current density for the zinc, 27.5 milliamps per centimeter squared, and the proton reaction has 10% of that current density. So we can solve. The important message here is that we have actually quite a high corrosion current density, specifically because there's so much extra area available for the cathode reaction. This is very important when we have bimetallic corrosion. In other words, what happens if we were to have a reactive metal connected to a large area of a more noble metal? That's exactly what we have in this situation, and it's a common engineering problem which we will look at in the next section on localized corrosion phenomena. Okay. Section 3.10 is a recap of what we have learned from the algebra of corrosion kinetics. There's a few comments to make. If I want to slow down corrosion, what can I do? So I can remove water. I can avoid being in the situation where I have to do electrochemical corrosion speed calculations at all. More likely, I can try metals which have a low exchange current density for the, say, for the proton discharge reaction. For example, zinc is typically used as a coating because it has a low exchange current density for the hydrogen reaction. If I have a different situation, if I have corrosion caused by dissolved oxygen, I can try to slow down the oxygen supply, either by somehow degassing the water or making sure that there's not a small boundary layer. Maybe I can have a slow fluid flow, which gives me a slower diffusion-limited oxygen supply. And I can try to avoid this situation of the area effect from the last section. I can try to avoid having concentrated anodes with a large cathode, which happens in practical situations like when you have an iron nail bashed through a very large copper sheet and then it's carelessly left out in the rain or something. I can try to avoid those situations. Anyway, section 3.10, you can read the summary as to important things to take away from the algebra of corrosion kinetics. Section 3.11 is then the last thing I want to say on passivation. This is the kinetics of corrosion when we have passive corrosion. Now, this draws on everything we've seen so far. We're going to use the pH potential diagrams, and we're going to use these Evans diagrams for corrosion speed, relating corrosion current density on the x-axis to the corrosion potential on the y-axis. Now, when you have a metal, say for example iron, which can undergo passivation when it put into a very oxidizing environment, we might have this situation shown by these two figures, 3.8 and 3.9. So consider starting with some iron, and it's in acid at condition A, and we gradually make the environment more oxidizing so that it undergoes active corrosion in region B. Eventually, in the very oxidizing environment, it becomes passive at point C, and then at point D, I'm imagining putting a very strong oxidizing environment onto the iron, and the question is, what happens to that? So, in the pH potential diagram, we can't necessarily say anything about the corrosion rate, but from what we now know about the Tafel equation, we can sort of write a plot of what happens to the corrosion speed of this steel. So this is what the right-hand side on the slide diagram does. So figure 3.9, the Evans diagram says that we start at point A. This is on the border of immunity with active corrosion, and the iron begins to dissolve at a slow rate. It starts off at the exchange current density, and it gets faster. We have Tafel-limited behavior in region B, so that as we increase the corrosion potential which is being applied to the iron, on this log of current diagram, we have a linear increase of log of corrosion current density with potential, until we reach point C, where at that point our Tafel-limited corrosion, which was this simple straight diagonal line behavior, suddenly the corrosion current density collapses down to a vertical line for region C, passive corrosion current, where we have just a fixed, very slow corrosion current density, which I've said might be, for example, 1 times 10 to the minus 6 milliamps per centimetre squared, a very slow rate of corrosion. And if the environment becomes more and more and more oxidizing, eventually we reach this region D, which is called a transpassive region of corrosion behavior. What this means is that environment on the metal surface is so oxidizing, the protective oxide film breaks down. This is sometimes said to break down mechanically, perhaps because of damage caused by oxygen bubbles being evolved. Anyway, in the transpassive region, in extremely oxidizing environments, we do expect the iron to once again start corroding rapidly. But over a quite nice passive window, we actually had this iron being quite slowly corroding and safe for use. Okay, so section 3.11.1, factors affecting passivation. So we've talked through there for iron how oxidation potential affects whether or not the metal undergoes this active-passive regime. Well, for iron, there is passivation because it's one of these metals that has a higher solid oxide, which is protective. Other metals, which, for example, like zinc, which don't have a higher oxide, might just undergo an immune to active behavior, which is much simpler. Nonetheless, iron is such an important one. If for no other reason than iron and steel, we need to know about active-passive behavior. Another thing which affects passivation is alloying. In passive stainless steel, the surface is often chromium oxide. Now, a pretty simple description of the effect of chromium is that you can imagine it expands the regions of passivity which are already present on the pH potential diagram for iron. Another way of looking at it, a more complicated one, is that you can say the stainless steel is passive if either the iron content is passive or the chromium content is passive. The overall effect is that in neutral solutions you certainly expect your stainless steel to be passive against corrosion because of chromium oxide. What else? Aggressive chemicals. Chloride ions are very important. These cause destruction of the passive films on many alloys. Those have the effect of shrinking the region on the pH potential diagram where there is passivity and increasing the area where you have active dissolution. And finally, abrasion and cracking. So it may be that when we have a very low passive corrosion rate, as I showed on the previous Evans diagram, we may have a passive corrosion current density which is actually rate limited just by the by the speed at which the solid oxide is abraded from the surface of the alloy. So frequently you can imagine anyway that being the rate limiting step for passive corrosion current density. Okay, good. The final part on page 40 is just a glossary of the algebraic symbols which I've used so far in the course, and where they can be found in this handout. In the second handout for this course, we want to go on to look at not just algebraic descriptions of corrosion, but what kind of real phenomena can we describe, partly based on the understanding that we have from this algebra. And once we know about some real corrosion behaviours, then we'll look at corrosion protection methods to try and stop them or slow them down. Okay, so that is what we will look at in the future.